proyecto de investigación Info Project y la carrera de Ingeniería en Tecnologías de la Información de la Universidad Nacional de Chimborazo, Ecuador, te invitan a participar en
Second International Congress Innovation Research and Technology in Information and Communication Technology, ICTAR 2022. Evento virtual a realizarse del 21 al 25 de febrero del 2022. Para más información, visita nuestra web ictor2022.unach.edu.es.
La carrera de Tecnologías de la Información surgió por la necesidad de contar con profesionales que ayuden al desarrollo sustentable de la sociedad en el campo de tecnologías de la información.
Estudia los principios, metodologías y estándares de calidad involucradas en el proceso de análisis, diseño e implementación de las tecnologías de información en un organismo institucional, en las áreas como son redes, programación, infraestructura, seguridad, base de datos y servicios web, lo que contribuyen al desarrollo productivo, local y nacional, así también como el acceso universal a la información y comunicación.
El objetivo de la carrera de Tecnologías de la Información es formar profesionales éticos, competentes y emprendedores con conocimientos prácticos y teóricos para diseñar, implementar y evaluar soluciones de tecnologías de la información. Otro de los objetivos de la carrera es permitir el acceso al conocimiento científico que es necesario para desarrollar las competencias profesionales que contribuyan al desempeño laboral en las áreas de redes, programación, seguridad de la información, infraestructura, desarrollo de software y aplicaciones web.
La Universidad Nacional de Chimborazo nos brinda varios servicios como son el uso de laboratorios y equipos de última tecnología, acceso a la plataforma, aula virtual y biblioteca. Tenemos también áreas verdes y espacios de recreación. Un servicio adicional, contamos con un incentivo a los estudiantes que obtienen el primero y segundo lugar al culminar cada semestre con las mayores notas. A eso lo conocemos como son las becas académicas.
Las tecnologías de la información se constituyen en la actualidad en un eje transversal para el desarrollo de las empresas públicas y privadas. Los estudiantes de la carrera de Ingeniería en Tecnologías de la Información, durante su proceso de formación adquieren competencias para el desarrollo de sistemas informáticos, aplicaciones web, aplicaciones móviles, inteligencia artificial, Big Data, la administración y gestión de redes de computadoras. Durante la formación en la carrera, los estudiantes tienen la posibilidad de trabajar en proyectos con empresas públicas y privadas de la localidad, lo cual les permite llevar a la práctica sus conocimientos adquiridos en las aulas y laboratorios. Invitamos a los estudiantes de los colegios para que apliquen a la carrera de Ingeniería de Tecnologías de la Información, que se constituye una oportunidad laboral que hoy en día las empresas están demandando una alta cantidad de profesionales con conocimientos en el área de las tecnologías de la información.
Te invitamos a formar parte de la carrera de Ingeniería y Tecnologías de la Información, en la cual tendrás una gran posibilidad de especialización. Tú podrás elegir lo que más te guste para especializar. Además de que también puedes formar parte de comunidades como la cual tenemos aquí de soft.net, la cual es una comunidad de Microsoft que te relaciona con comunidades tanto internacionales como nacionales para mejorar tus conocimientos. Ven, te invitamos.
Desde el modelo constructivista del aprendizaje, el docente entrega su protagonismo al estudiante, quien asume el papel fundamental en su propio proceso de formación para alcanzar la transferencia de la teoría a la práctica en una atmósfera que invite a todos a investigar, aprender, a construir su aprendizaje. El rol del docente es el de realizar un acompañamiento cognitivo, comunicativo, afectivo y social para que nuestros estudiantes tengan la capacidad de transformar el entorno que les rodea a través de acciones que les permitan ir superando obstáculos y desafiar el reto que implica su formación integral y así lograr insertarse en la sociedad del conocimiento.
Ven, sé parte del futuro. Estudia Ingeniería en Tecnologías de la Información que cuenta con aulas y laboratorios de última generación, facilitando así tu aprendizaje y desarrollo académico.
Mi nombre es Andrés Ochoa, soy graduado de la Universidad Nacional de Chimborazo, en la carrera de Ingeniería en Tecnologías de la Información. Actualmente me encuentro laborando en la ciudad de Quito, en la empresa de NetBuy Consulting Logic Studio. Les hago la cordial invitación a que ustedes formen parte de esta maravillosa carrera como es Ingeniería en Tecnologías de la Información dentro de la Universidad Nacional de Chimborazo, ya que fue pilar fundamental para mi formación y para lograr mi objetivo en el cual me encuentro actualmente laborando. Ustedes también pueden lograrlo, los beneficios de la carrera son increíbles, pueden hacer un trabajo remoto tanto en el país como fuera del país. Es una carrera bastante demandada y que les va a ayudar a cumplir todos sus objetivos.
Muy buenos días con todos, dándoles la bienvenida al último día de este congreso IC Talk 2022. Les agradecemos su participación por toda esta semana. El día de hoy vamos a tener la participación de Sana Soltari. Vamos a darle una pequeña introducción y el doctor Luis Tello estará a cargo. Welcome to Sana. Thank you so much to be here and be part of IC Talk 2022. Dr. Luis Tello will give an introduction about you. Thank you so much to be here. Go ahead. Thank you. Luis.
Okay, thanks so much. Good morning, everyone. Thanks for attending this conference, IC Talk 2022. Well, today we have the pleasure to present Master Sana Soltani. Continuing with the talk, she will present the topic Security of Topology Discovery Service in Software-Defined Network. Master Sana is a PhD student in network security at the 5GIC and 6GIC Innovation Center, University of Surrey, UK, under the supervision of Dr. Mohammad Shohafar and co-supervision of Professor Rahim Tafazoli. Her research interests are network security and privacy, network softwareization, and network function virtualization. She has 7 years of working experience as a mobile network specialist in international telecommunications companies such as Huawei and MTNI RAN Cell. So please join me in welcoming Master Sana Soltani.
Thank you so much. Hello, all. And I'm so happy that I'm here for this presentation. Let me share my screen. Could you see my screen?
Now we can see your screen. Thank you.
Okay. Thank you so much for providing this opportunity for me. This is a presentation about security of topology discovery service in software-defined network. The content of the presentation could be divided in 4 parts. In first part, we go through the introduction part, and then we start the state of the art and the previous study which had done in this study. Then we discuss the proposed solution, and after that we go through the conclusion and future research plan. First, let's start with introduction. Topology discovery service in SDN. We know that the SDN architecture Could you hear me now? Sorry.
Yes, we can hear you.
Okay. The SDN architecture could be divided in 2 parts, data plane and control plane. SDN controller is the brain of the network and needs to have some information regarding the data plane because the SDN controller wants to make some decision about routing, mobility management, and other network activities. So because of that, a topology discovery service module is provided and defined in SDN controller. The responsibility of topology discovery service, or TDS, is to provide the topology information for SDN controller and help the SDN controller to make a correct decision. For example, when a new switch is connected to the network, the initial handshaking process is started, and the TDS, I mean this module, capture the information regarding that switch and also the new link. There are 2 critical modules in TDS. One of them is host tracking service, and the other one is link discovery service. The host tracking service is responsible to track the location of the host in the network. And the link discovery service is responsible to identify the link between two different switches. So by using these two modules, I mean host tracking service and also link discovery service, the SDN controller could capture the topology information from the data plane. But the question is that why TDS is important, why topology information is important for the SDN architecture. Because the topology information is used for many difficult applications. I mean, the network applications such as packet routing, mobility management, congestion management, and also load balancing. All these applications use the topology information in order to do their responsibility. So TDS is important for the SDN architecture. We know that the TDS is important, so we should protect the TDS against the different type of the attack. A well-known attack against the TDS is topology poisoning attack. This attack could poison the controller view regarding the topology of the network in the data plane. Topology poisoning attack could be triggered in three different scenarios. In the first scenario, which is related to the switch, the adversary injects the fake link to the fake switch to the network and poison the controller view regarding the number of the switch. The second one is host location hijacking attack. This attack take over the IP address of the victim host and do some malicious activity by the victim host. The third one is related to link fabrication attack. In this attack, the adversary aims is to insert a fake link between two switch, I mean the fabricated link. And by this action could change the route of packet forwarding and could change the route of the traffic. So we could see that the impact of the topology poisoning attack is high, and we could categorize it as a high risk area because it could severely impact the performance on the performance of the topology dependent service, as I told, packet routing, mobility management, and congestion management as well. It also could cause some backhaul in the network and maybe degrade the quality of the service and directly impact the end user. So we could protect the SDN architecture from this kind of the attack, I mean topology poisoning attack. So the impact and cost of the topology poisoning attack in SDN architecture is very high, and we should protect the topology discovery service against the different type of the attack. So based on this motivation, we do some studies, and we realized that the current defense, existing defense against topology poisoning attack suffer from some vulnerability. I mean, some critical aspects, some critical security aspects are not met in these defenses. Some of them are mentioned here. For example, some defense works only based on the single threshold, and this single threshold could easily bypassed by the attacker. And the other gap is that the current defense only could work in a static environment. I mean that in the dynamic environment, when the new switch is joined to the network and the topology is changed, the current defense could not work properly. And the third one is that the existing defense could not support the real world use case. For example, if we had the distributed SDN in the real world use case, the existing defense could not support them and could not detect the topology poisoning attack in this situation. So based on this motivation, we conduct our study on the topology poisoning attack and also topology discovery service. In this part, we are going to review the state of the art and discuss about the different attack and also different defense. First, I need to start with link layer discovery protocol. This is a protocol that SDN controller use in order to collect the information from data plane, I mean capturing the topology information from the switch. By using LLDP, SDN controller could realize that the switch and the connection between them. In this protocol, the SDN controller send LLDP packet toward the switch in data plane layer. When the switch receive LLDP, for example, in this case, when switch 1 received the LLDP from controller, broadcast it through all its ports. So the switch 2 received the LLDP packet and forwarded toward the SDN controller. When SDN controller received the LLDP from switch 2, realize that there is a link between switch 1 and switch 2. And this is the procedure that the controller repeated in a specific interval. For example, in the floodlight controller, it repeats every 15 seconds. But LLDP, I mean link discovery protocol, has some vulnerability that could be exploited by the link fabrication attack. In a link fabrication attack scenario, we suppose that we have two hosts, host 1 and host 2. And these two hosts are compromised by the attacker, and the attacker provides the out-of-band channel between host 1 and host 2 to relay the LLDP packet. In link fabrication scenario, SDN controller send the LLDP toward the switch. When switch receive this LLDP packet, send it toward all its port, so host 1 receive the LLDP packet. In a normal scenario, when host 1 receive LLDP packet, ignore it. But in this scenario, because the attacker has the controller of the host 1, it receive it and relay it through the out-of-band channel. So host 2 receive the LLDP packet and send it toward the switch. Switch 2 receive LLDP and send it toward the controller. Now controller receive the LLDP packet from the switch 2, and the controller realized that maybe there is the link between switch 1 and switch 2. As you could see, this is not the real link, and it is a fake link which is created by the adversary. This is all the scenario about the link fabrication attack. The use case of link fabrication attack is could be in the vehicular network. As you could see in the vehicular network, we could consider the vehicular as an end user and also edge server as a host, and RSU could be considered as an open flow switch. And by launching the link fabrication attack in the vehicular network, the KPI of the network could be seriously impacted. For example, we could have low service success rate and high packet loss. Another use case would be in the data center. I mean, in the data center, the different switch in different layer could be compromised by the attacker, and the fake link could be created between the different switch in the data center as well. There are different type of the defense against link fabrication attack, but the most well-known is TopoGuard and also the TopoGuard Plus that we discuss about them. The first one is TopoGuard. TopoGuard use labeling strategy in order to detect the link fabrication attack. In the labeling strategy, the TopoGuard Plus label each port which is connected to the host. I mean that for each port which is connected to the host, TopoGuard Plus label that port as a host. And the story is all about the TopoGuard. And the TopoGuard set a rule on the SDN controller that the controller could not accept any LLDP from the host. I mean that when the controller receives one LLDP from host, it should reject it. So when host 2 host 1 relay the LLDP toward the host 2, and host 2 send that LLDP toward the SDN controller realized that this LLDP is received from the host 2. So it rejected and could not accept the LLDP. This strategy, I mean the strategy which is used in TopoGuard, could be bypassed by the port amnesia attack. In a port amnesia attack, what the attacker did is that resetting the port before sending the LLDP. So when attacker received the LLDP, first reset the port, I mean the port which is connected to switch 2, and then send the LLDP. By this activity, the labeling is disappear, and the controller could not realize that the LLDP is received from a host and accept the LLDP. So the link is created between switch 1 and switch 2. Another defense is TopoGuard Plus, which is the most well-known defense against link fabrication attack. TopoGuard Plus used the link latency strategy in order to detect the attack. We know that the attacker used the out-of-band channel between two switches. And we know that the latency of the out-of-band channel is greater than the latency of the normal link. So the TopoCard Plus firstly add a timestamp to LLDP and send that LLDP toward the switch. And when receive this LLDP, extract the timestamp and calculate the TLLDP. TLLDP is the duration that takes the STM controller send one LLDP toward the switch and receive it from another switch. This duration, we call it TLLDP. Also, STM controller capture the latency between the controller and the switch. For this case, STM controller repeatedly send the probing packet toward the switch and calculate the latency between controller and the switch. We call it TP1 and TP2. You could see that by a simple calculation, I mean TLLDP minus TP1 and TP2, we could calculate the latency between two switch, I mean TL. TopoCard Plus monitored this TL, I mean latency between the switch for a while, and after that could realize and could identify a threshold for the link latency. So if the controller receive one LLDP with the latency which is greater than the threshold, the controller should reject that LLDP. I mean that the strategy of the TopoCard Plus is to identify a threshold and reject any LLDP which has the latency greater than the threshold. And this is the strategy that TopoCard Plus used to detect the link fabrication attack. But this strategy, I mean the TopoCard Plus, could be bypassed by the link latency attack. Link latency attack is the attack that we propose in this study, and this attack could easily bypass the TopoCard Plus and inject the fake link between two switches. In this part, we are going to discuss about our solution and also our attack that could bypass the TopoCard Plus. Our contribution is that we propose the link latency attack. That could successfully bypass the TopoCard Plus and inject the fake link between two switches. And also we develop a machine learning based defense system that could protect the STM controller against the link fabrication attack and also link latency attack. Our assumption is that the adversary could compromise one or two hosts, same as the other studies, and also the adversary provide an out-of-band channel between two switches. The problem is that the adversary wants to add a fake link between two switches, and we suppose that the TopoCard Plus is already present and is already implemented on the STM controller. And our purpose, I mean, as an attacker, is to bypass the TopoCard Plus. The solution is link latency attack, which is included two phases. The first one is overload phase, and the second one is relay phase. What happened in the overload phase in link latency attack? As we discussed, TopoCard Plus use TLLDP, TP1, and TP2 calculation in order to detect the fake link. If the latency of the link is greater than the threshold, the TopoCard Plus realized that there is a fake link between two switches. We know that the adversary used the out-of-band channel, and the latency of the out-of-band channel is greater than the latency of the threshold. So we want to decrease the latency of the out-of-band channel. I mean that we want to decrease the T out. We know that T out is calculated by TLLDP, TP1, and TP2. If we want to reduce the, if we want to decrease the T out, we could increase TP1 plus TP2. So we use this strategy. I mean, our aim is to increase TP1 and TP2 in order to decrease the T out of band channel. If we could decrease the T out, I mean T out of band channel, so we could bypass the TopoCard Plus threshold and we could inject our failed link. For this purpose, I mean increasing TP1 plus TP2, we use overload phase in LLA. But what is overload phase? Overload phase. In the overload phase, we use ARP traffic, I mean a huge amount of ARP traffic in order to overload the switch 1 and switch 2. For this strategy, we send a huge number of ARP traffic toward the switch in order to make the switch overloaded. By this action, the switch received a huge number of the packet, huge number of the packetting is generated, and sent toward the controller. When the controller sends the probing packet toward the switch, this probing packet takes more time to be processed. And by this case, we could increase TP1 and TP2. I mean that the RTT round trip time is increased, and based on that, TP1 and TP2 is increased. So the TopoGuard Plus maybe realized that there is some increase in the value of the TP1 and TP2. This is all the things that we want to do in overload phase, increasing TP1 and TP2 by sending the huge traffic toward the switch. This duration of the sending huge traffic is only for some 1 or 2 seconds, and it could not realize by the TopoGuard Plus. The second phase is relay phase. After overload phase, we increase the TP1 and TP2, and then we start the relay phase. In the relay phase, the host change their rule from the sending the R packet to listener. I mean that in this phase, when host 1 receive the LLDP packet, relay it through the out-of-band channel, host 2 receive it and send it to the switch, and switch again send it toward the controller. When controller receive that LLDP packet, because TP1 and TP2 is increased, based on the calculation, the latency of the link is less than the threshold. So TopoGuard Plus accept the LLDP and add an example of the this example of the running our attack on a TopoGuard Plus. As you could see, first we run the TopoGuard Plus controller, and as you can see in the picture, we have two switch 1, and we have 3 switch 1 and switch 3 is not connected at first, but when we launch our attack, we could see that the fake link would be inserted between switch 1 and switch 3. In this snapshot, in first part, you could see that the interlink switch is identified. As you could see, the interlink switch, let me show my pointer. You could see that the delay of the delay or latency of the link is nearly 5 milliseconds, and the threshold is nearly 6 milliseconds. This is the normal case. I mean the normal LLDP and the normal detection with the TopoGuard Plus. In the second phase, we start the link fabrication attack, and you could see that the TopoGuard Plus could detect the attack because the latency is greater than the threshold. So TopoGuard Plus raised some security alarm and informed the admin that some attack might be happen. In the third section, you could see the latency between the controller and the switch. It's less than 1 millisecond. In this stage, we start our attack, I mean link latency attack. We first start with overload phase. In the overload phase, you could see that we increase the TP1 and TP2, and the latency of the TP1 and TP2 reached to more than 100, I mean 130 milliseconds. And after that, after increasing TP1 and TP2 only for 1 or 2 seconds, we start the relay phase. In the relay phase, you could see that the new link is added to the network, and TopoGuard Plus could not detect the link latency attack, and the new link is added between switch 1 and switch 3. By this snapshot, we show that the TopoGuard Plus could easily bypass by the link latency attack, and the attacker are able to insert a fake link between 2 switches. Our second contribution is to provide the machine learning link guard that could detect the link fabrication attack and also link latency attack by using the technique, I mean outlier detection technique in the machine learning, by using the machine learning technique. First, we provide our data set. For providing our data set, we run the controller for nearly 3 days and capture all LLDP in the network, I mean in 2 different situations. The first one is the attack-free environment, and the second one is the attack environment. We launched the different attack of the link fabrication attack and link latency attack, and after that we captured the LLDP packet. And based on the data set that we provide, we run our machine learning, we train our model, and also we test our model. We select 3 features for our machine learning, TLLDP, TP1, and TP2, and based on these features, we train our machine learning, supervised technique, and use the different type of the supervised machine learning to detect the attack. In this picture, you could see the architecture of our defense. SDN controller, as we discussed, periodically send the LLDP toward the switch and then receive this LLDP after a while. When SDN controller receive one LLDP, extract some information from that. These are TP1, TP2, and TLLDP. And then send these parameters to machine learning classifier, which is our defense. And based on this classifier, which is trained based on our data set, we could realize that that link is related to the fake link or valid link. If it is valid link, the SDN database would be updated, but it is a fake link, the security alarm would be raised and the SDN controller reject the LLDP. This would be happen for all the LLDP packet which is received by the SDN controller. And this is the algorithm and the detail of the MLLG. This is a result for our defense, and based on a ROC plot, we could realize that between the different machine learning algorithm, KNN have the best performance and could detect the more attack in compared to other machine learning. And if you could see here, actually TopoGuard Plus have the accuracy of the 84%. However, our MLLG defense for the KNN have accuracy of 98%, which improved the accuracy. And also for false positive rate, the false alarm, we could see that our defense has the less false alarm in compared to TopoGuard Plus, and also the TPR, the recall and attack detection rate is so high for the machine learning case, but the TopoGuard Plus has a less value, and this is because that the TopoGuard Plus could not detect the link latency attack, and in detecting link fabrication attack, the machine learning algorithm could work better than TopoGuard Plus. And also the F1 score is calculated, and you could see that the machine learning has best result in compared to other defense. In this part, we discuss about the future research plan and also the conclusion. Our result, the contribution for the link latency attack and also our proposed defense is published in IEEE CNSM 2021, and actually it's published in October 2021, and this is the result of our contribution. For the research, future research plan, we could extend machine learning link guard, our current defense, to cover and support the new requirement of the network. For example, in some network, the network topology might be changed frequently, or in a dynamic environment, some new requirements are raised. So we are going to extend our machine learning to cover and could address this type of the request. Extending the machine learning link guard to support the more dynamic environment. Also, we are going to extend our work to support the multiple controller. In the real case, in a real world use case, sometimes we need to use the distributed SDN in the flat distribution or in the hierarchical distribution. So we are going to extend our work to cover also the different SDN architecture. And also at the end, we need to investigate the risk of topology poisoning attack in some the real world networks such as 5G network, SDN-based 5G network, and we check the risk of the topology poisoning attack in this architecture. And these are the reference that we study and use in this presentation. Thank you so much for your attention, and if you have any question, I would be happy to discuss. Thank you.
Thank you so much, Anas, for your excellent presentation. The topic was very clear, Well, we have some questions regarding the signaling that is added when once you implement this solution. So could you elaborate a little bit on how the signaling will impact the topology of the network? And for instance, the delay also can be impacted by the implementation, right?
Uh, um, I couldn't get the point about the signaling. You mean that?
Yeah, I mean, for instance, if you once you implement the machine learning solutions
Yeah.
to communicate the optimal parameters, right? You should have to send some feedback to the network so that the network can adapt to these parameters.
Yeah, you know that the LLDP protocol is completely work on the signaling part. I mean that it's not related to traffic part. It's completely related to signaling part. And based on the signaling message that the controller receive could detect that if there is a link between the switch or not. So we implement our defense on the SDN controller. So when controller receive one signaling message, I mean in terms of LLDP packet, first check if the latency of the link. If the latency of the link is in the variable, is in the acceptable rate, I mean the machine learning check that one, because the machine learning learn based on the normal behavior of the network and know that in this situation, the latency should be in this interval, for example, the specific interval. I mean that the controller all the time work with this signaling message LLDP, because our data set is trained based on the signaling message and specifically based on the LLDP signaling message. Yep.
Okay, thanks so much. And what about to look for another KPI metrics in the network? For instance, there is actually a novel metric that is called age of information that can have it's like an improvement of the delay. So how can we address these kind of solutions for novel topologies in 5G or 6G networks?
Yeah. If you know, the architecture is based on the 5G network or 6G network, you know, first of all, the architecture should be based on the SDN controller. I mean that we had the controller and also other nodes in the 5G or 6G, which is connected to the controller. For this part, we could implement it in both layer. I mean, in the access layer and also in the core layer. If we could consider in the core layer, we could consider the, for example, the UPF nodes such an open flow switch, and the link between the UPF, we could consider that link as a link between two open flow switch, because in the 5G based SDN based 5G network, we could simulate the UPF with the open flow switch. And sometimes when the attacker has compromised some host in the network, could create a fabricated link between the UPF, and you know that the user traffic is routed based on the UPF, and if some malicious link is added between two UPF, this traffic could be impacted. I mean, the route of the traffic. Yeah, for the 5G network, we think about that one, and this is our future work that we tested on the UPF based on the SDN-based 5G architecture. Yep.
Okay, thanks so much.
Welcome.
And finally, this solution can be implemented using IPv4 or IPv6. Is there any impact on the network if you consider a different protocol, routing protocol? I mean?
You know, this type of the attack and also the defense is applicable for the SDN environment at the first stage. because the SDN controller use LLDP protocol to capture the topology information. If you choose that, if you change the architecture, or any the strategy of capturing the topology information, this attack might not be applicable for that one. But for this case of the attack, link fabrication attack, it is only based on the LLDP. And if any architecture, any network topology use the LLDP protocol in order to detect the link between the switch, this attack is applicable for that architecture and could be happen. And also the defense could be used. The first thing is that it should be the SDN based, and the second one is that it should be managed by the LLDP protocol. Yeah, if we have these two cases, actually this attack could be happen, and also the defense would be applicable for that one.
Okay, Sanas, thanks so much for answering
thank you for your
questions.
question.
Yeah, thanks so much. And with that, we finish this presentation. So we want to thank the public for hearing Sanas, and that's all. Thanks so much.
Thank you so much for providing this opportunity.
Thank you so much, Sanas, and I want to give also thank you to Professor Mohamed Jojafar, because we have the chance to know about you and know about your work, that we know that is very prestigious and you are publishing very good papers. I want to say to you, give you lucky to you for your work. Thank you, and thank you to Professor Mohamed also.
Thank you so much.
I hope to have you in the next time also. Thank you.
El proyecto de investigación Infoc Project y la carrera de Ingeniería en Tecnologías de la Información de la Universidad Nacional de Chimborazo, Ecuador, te invitan a participar en
Second International Congress Innovation Research and Technology in Information and Communication Technology, ICTOR 2022. Evento virtual a realizarse del 21 al 25 de febrero del 2022. Para más información, visita nuestra web ictor2022.unach.edu.es.
La Dirección de Posgrado de la Universidad Nacional de Chimborazo oferta el programa de maestría Auditoría de Tecnologías de la Información, una maestría académica con trayectoria de investigación dirigida a profesionales con títulos de tercer nivel en áreas como sistemas, informática, tecnologías de la información y otros campos del conocimiento relacionados con las TICs. Ven y sé parte de la maestría académica con trayectoria de investigación, Auditoría de Tecnologías de la Información.